kilogram than gasoline. That's how, that's what you're up against, trying to convince people to recycle these things, when economically and from an energy point of view, you can get so much out of them by just burning them. And that's something that will have to change in the future. I also give some very brief background information about different polymer manufacturing techniques, which I take from the process universe, and show students how you can go from an individual materials record to relevant processing records using the links in the program. And I talk about very common polymer processes: injection molding, blow molding, foaming, and polymer casting and extrusion. I'm not going to go into much detail, but these are just images I've taken from the EduPack entries, just to show you the kinds of things I'm showing the students. I don't go into a lot of detail because I don't have time in a single lecture to do this, and I only have one lecture to do everything in the course. So to summarize, in my single lecture, which in interest for you guys is 90 minutes in many Swedish universities, I show how plastics have developed and likely future trends, why we use them, and why we can recycle them, but also why people might want to burn them instead, even if it sounds a bit like a waste, as well as giving them information about manufacturing routes. If I did have more time and I wanted to deepen the use of EduPack, for example, I could start using things like eco-audit, replacing glass or metal containers with plastic containers. And there are some case studies of this. I assume they're still available from the Education Hub, or the case study about replacing steel with reinforced composite in a truck, for example. Look at chemical compatibility, also information that's available in the database. We use plastics for containers because they're relatively inert. They don't react with a lot of different things. And also think about the sustainability of the supply. I didn't have time to do any of those three things. Information is there in EduPack to do it, but I had to limit myself to a 90-minute lecture, so I couldn't actually do that. But that's something I would definitely consider in the future. I think that's pretty much all I have time for. I realized that was a bit quick, but I hope it gave you a sort of a flavor of how I've used the software in my lecture and why I've done that. So I'm happy to answer questions at the end, but until then, I'll stop sharing my screen. I'll pass back to Lizzie for Richard to take over.
Thank you very much, Chris, for this very interesting presentation. Yes, I think we'll keep questions for the end, but just as a reminder here to please put your questions in the chat. And I think I'm going to hand over to Rich now.
Hopefully you can read me now.
Yes, we can hear you.
I've not yet got my. Can you see my blackboard or green?
Yes, we can hear you and can see your blackboard.
Okay, thank you so much. Thank you so much. Once again, thanks for having me, and thank you, Chris, for that journey into sustainability with plastics, which is really where the focus right now is in plastics, not only because of traditional polymer processing evolving more and more, but also with makers making more and more use of plastics. And in order to get my students acquainted with the work makers do and how they can work as makers themselves, and in order to get the polymer world into this maker world and establish it in a better way, I put together a program which is run under the headline of Advanced Material Science. But eventually, what I made out of that was a project where people work with a cheap 3D printer, with one of those Ultimakers, which I will show you in a minute, and where they integrate textile structures into 3D printing. And why textile structures? Because textiles, that's where my students come from. They all would-be textile engineers, and they more or less deal with plastics in a general way, whilst they are focusing on their fibers, they might have a look into how fibers are extruded from and spun from polymer materials, but they won't deal with polymer processing at all until they get confronted with me and my makerspace, my small makerspace, which I've got. So when I do this, I just told you when I introduced myself that I work in the south of Germany and the southwest rather, in Reutlingen, which is situated about 30 kilometers to the south of Stuttgart. Okay, and we've got about 5,000 odd students of them, and all of them get confronted with 3D printing during their study programs, during their degree programs. All of them under different aspects. There's the chemists, the information technology department, there's the business department and logistics department, they are dealing with that, and us in the textile department. So there's quite a lot of different approaches which you can find, and the one I chose was to get students acquainted with that in a way that they can help themselves later on when they leave the university. So what I do there is what universities of applied sciences, as they are called in Germany, what I call universities of youth sciences, sorry, forgive me for that, but it's them being able to apply what they have learned in a practical way with practical results. And in order to do that with people who are not so deep into material science or even more shallow in polymer science, I try and convert what I have learned and what other people around me have learned into what I call Swiss knives and maps. Maps is one of the central things which you need in your backpack once you go into the jungle and once you try to explore new areas. And that's what these makers do on an everyday basis. So maps is something where you, even if you are not so familiar with the geography, you can find your way forward. And Swiss knives is what you need if you have to do the one or the other quick fix, or the one and the other step where you cannot make use of a completely equipped workshop. So that's what we try to do together, my former student, Kumar Rahul, and myself. And this is just the first step. The next step will be to gamify the whole thing, so as to people explore a virtual materials world with their Swiss knives and the maps. Then, of course, the maps, the role of the geographers or the surveyors is played by my dear colleagues, by my dear friends from ANSYS, Granta, because the Ashby charts are exactly what you need if you don't want to go too deeply into metal science, into polymer physics, and so on and so forth, but you want to find your way forward, finding the right materials for the right application. And that's what I want to illustrate a little bit and put forward to you for discussing later on at the example of this project, which I just mentioned, this project which is dealing with using 3D printers, the cheap ones, the fused deposition modeling with textiles. So just to give you an idea about what sort of process that is, you have a reel. On the reel you find a filament made of plastics, of one of those plastics which Christopher just mentioned. For instance, PLA. PLA is one of the most important polymers for makers. And then this PLA filament is pulled by some gear wheel construction, is pulled into an extrusion and heat unit. It's heated up to a temperature above the melting temperature, and then it's pushed by the filament itself. It's being pushed. The melt is being pushed through a nozzle, onto a platform, and then layer by layer by layer is printed, so to speak, or extruded on this platform. So that's what people work with, and here they are. And in the beginning, I asked them what they want to do, and they have a session on ideas, what they could do, what sort of useful things they could provide the world with. And this time it was making a case. So it's the ideal subject for a case study, making a case, creating a case for idea cards and things like that, based on this semi-flexible material, combination of textiles and 3D printed polymer structures. In order to get them acquainted with the material we have at hand, of course, we use the data sheets from Branda EduPack. And here you find an excerpt. So what they find is not only the material as such described in a scientific way with the mechanical, thermal, and chemical properties, but also where they can get hold of that, which are the suppliers. And as Chris just told you later on, they can also make their own study on the ecological viability of such a project. Okay, the first Swiss knife I get them acquainted with in this process is to choose the layer thickness of their print. You remember, the print is done layer by layer. There's slices of the material printed on upon each other, and you can imagine the coarser the layer, the faster you are, and the faster you are, the less of a contact there is between the various layers, and the less of a contact there is between the various layers, the worse your mechanical properties are. So there's the trade-off, mechanical properties versus print parameters. And that's something which is far away, at first sight, far away from where Granta works, where the EduPack works, but it's rather close, as I'll show you in a minute. What we did in that respect was some quite deep scientific research into this filament process, and we did this together with my dear colleague Vladimir Kuznetsov. He's one step ahead of myself. He's got a fab lab of his own, a fab lab which, in difference to, I think, most of the fab labs of this world, is embedded, so to speak, embedded in the material science, in the metallurgical unit, actually, Chris, in the metallurgical unit of Mises University, which you find at Rimsky Val in Moscow. People who are not so familiar with Moscow, they might be familiar with Gorky Park. So it's next to the park which 30 years ago in the Soviet times was named after Gorky. So, and with these people, we did the research which I will present you in a minute. This is the head of the laboratory, Vladimir Kuznetsov, with his masterpiece, I would say. It's a Printzilla, which can print 2.5 meters or 2 meter high structures in FDM, which is unique worldwide. We did a joint paper on this, which you can find in Polymers. It's about the relationship between the geometrical parameters, as I told you, and the strength of a structure, which is, of course, very, very important if you want to use the structure. And what we found out was, okay, the structure is quite different in its character, in its geometrical characteristics, if you use a very slow process with very small layers, as you see on the right hand, and very fast and very coarse, as you see on the left hand. It's the same machine, it's the same material, it's just the print parameters which are different. And what we found out was that there is a relationship between the mechanical properties, which you can see here, You have the nozzle diameter over layer thickness on the x-axis, and on the y-axis you have the ultimate strength as measured in a bending test. And you see that at the beginning, at a very fast pace, and then a little slower pace, you approach the actual parameters which you would find in a decently, I would say, decently injection molded sample of the same geometry. So there is this possibility, this opportunity with this process to go onto a quality level which makes it equal or at least comparable to injection molded part, which is very interesting for the students in future. So they see they can use that for a quick concept, which would be number 1, or nozzle diameter over layer thickness 1, as I depicted it. Here I have a cross section, yeah. Or if you take a longer time, you can use the same machine, the same material, to have a product which is applicable. So I won't go into that. This is another person, another colleague from Moscow, Mrs. Yaroslava Barmienkova. She's a designer, and she got me acquainted to this integrated structures. So it's sort of a composite of a 3D printed structure, FDM printed essentially, and then a textile, and then another few layers of 3D printed material on them, which creates a, on the one hand, very flexible material, very flexible objects, and on the other hand, you have the at least the mechanical strength of the plastics used. So that's that. And in order to integrate textiles into a print, into an FDM print, you have to choose them carefully. And the textiles have to fulfill certain requirements. One of them is obvious. It's the temperature. The melting temperature of the textile fibers should be well above the temperatures at which you process your filament, so as to not to melt or shrink in a significant way the textile which you want to integrate, and not having a lump later on instead of a textile. So that's the one thing. And on the other hand, you want to have a plastics material which is solid in a normal human environment. So that means that the glass temperature and or the melt temperature of your polymer should be well above, say, 50 degrees centigrade. So that's where you can use the maps provided by the surveyors, so to speak, the so-called surveyors from Granta EduPack, and you have the glass temperature as the longitude and the melting point as the latitude on this Mercator projection of materials, and then you find out, okay, if I can use nylon, for instance, PA66, or polyester fibers, no problem to use them with a PLA material in a FDM machine. So that's the way you use the map. And then there's a tricky one, which at first glance, you don't get any help from EduPack. And it's the problem, or the characteristic rather, of polymers, that they're extremely time dependent in their properties. You know this if you've been to a dentist or a stomatologist, and then have you had your jaws repaired and got a screw in your jaw is made up of a composite material. And if you put a metal screw in it, the dentist must see you back after 2 days or so in order to fix the screws a little bit, turn them a little bit more. Why? Because in the meantime, the jaw material, the polymer material in the jaw has relaxed and got acquainted with the screw, and now it becomes loose. Okay, and the same happens with your polymer material and in use. And in order to take that into account, we have, without having too much of a knowledge about the material behavior, just having the EduPack database at hand, you take the following way. So you would need this time frequency response. You would, if you want to make it perfectly, you would have a diagram, such creep diagram, but you don't have that usually. If you don't take millions of tons of a certain plastics, you won't get a stress strain or isochronous strain diagram, which you would need for this. So you must find another way. And one way to create the Swiss knife and to have this time information is to go into, I will just make that short, to go into your stress strain diagram and find out what information you find about this behavior, time-dependent behavior of your own material. And I'll just show you the difference between a metal or a Hookean behavior, which is instantaneous response. You put some stress, which is sigma, onto the material, and you have an immediate answer, a certain deformation, which will stay stable over time. With polymers, you have this stretched exponential response, as it's called. It's starting very fast, like a Hookean, and then it sort of retards itself and takes longer and longer times, but still creeps on. So that's been described, by the way, by a guy called Kohlrausch with this approach, and then it has been refound by Williams and Watts. So today, this behavior, this time behavior, is called the Kohlrausch-Williams-Watts response. But my students usually fall asleep when I try to explain to them how necessary that is for them to know, and so on and so forth. Therefore, I try to find a shortcut for them, and I found this in Granta. The shortcut is as follows. You use the yield strength, or the ultimate strength of the material, and the elongation at that stress, the yield stress, and then you take the modulus, the Young's modulus, and then you have two points of your stress strain curve, and you use these two stress strain coordinates to which you find in the EduPack, to create your, or to calculate your time dependence, to find this stretched exponential power. It's a fractional power in an exponential curve, which is really complicated, but you find it from these two parameters, and then lo and behold, you get it from yield and Young's modulus, and you can even find it for all of the materials which you have at hand, and you find out that it's not only useful for one and the same materials to describe its usefulness for your purpose, whether it reacts in a quick way or in a very slow way. Mechanical stress is quite important for its usability in certain environments. And here you see that for the normal exponential answer, you will have the almost all of the foam materials. And for the elastomeric materials, which you find here, you have 0.1, 0.9, 0.8, 0.7, 0.6 is the power which you have to describe the time behavior the time response of these rubber materials. And the idea is now to put this Swiss knife, as I would call it, directly into the database, so as to have the people who are really making something needn't take too much of a theoretical load of knowledge into their backpack, but can just have this Swiss knife, which easily calculates from 2 parameters what they have to expect in terms of the answer. So you can go with these parameters here, with these powers, fractional powers. You can go directly in your into your Kohlrausch-Williams-Watts curve, and then you can create all of the time response depending on the stress and times which you want to know about in your application. And that's quite enough for a maker to know. So she or he can find their way forward and choose the materials which they really need. So to come to a conclusion, for Swiss knives and maps, for 3D printing textiles, I think it's just 3 of the examples which I wanted to, which I have. There are more Swiss knives made based on the data and based on the structure of the database of Granta EduPack. They provide useful data, diagrams, and algorithms. You can put these maps together in a way, as I said, projecting your needs, your actual needs in terms of material knowledge into these maps, and then easily find out, even if you are not so familiar with the various materials, find out which is the one which you should pick for certain projects. Well, choosing an appropriate filament and calculating the strength is quite easy, and what I'm very fond of is that we now have a tool where we can at least roughly estimate the time behavior of the material, and that's what I wanted to share with you, and that's what I bombard my students with, and of course they're quite happy that they can use the Swiss knives instead of studying with my help, studying all these Kohlrausch-Williams-Watts relaxations and so on and so forth. And the only thing left of the relaxation phenomena of polymers is just they can relax with their Swiss knife at hand. So that's what I wanted to share with you today, and I'm open for your questions right now. Thank you so much.
Thank you, Rich, and thank you both, Chris and Rich, for your very interesting presentations. Harriet, I think, would you like to, there are a few slides that you wanted to go over? Should I?
Yes, you should have control back again now, Lizzie. So I, again, just want to echo what Lizzie said. I think we've had a great presentation from both speakers today, both Richard and Chris. Thank you ever so much. Hopefully, Lizzie, you can share some screen quickly. I mean, I'm just going to whiz through the community update, which we usually do at the end of a webinar. I really just want to say this quick because I've got a few questions coming in, and thank you for everyone who has already sent them through. This is just a quick update to just remind everybody that you can keep up to date with our activities and stories such like this on our ANSYS blog. On the next slide, I think we highlight for those who went to Simulation World that you can still see some of the sessions on demand. We have a few materials ones in there as well, which is great. And something that is quite good actually is the AIC courses that we're running, and we've just got our first course up for materials. So whether you're a student, a professional, lifelong learner, it doesn't matter really. These are free courses, and if you're not familiar with materials and perhaps some of the selection, then you can go and check this out in our materials AIC course. But I think we'll just jump straight into a few questions that we have time for at the end here. If you want to keep on sending the questions over, please do, and we can try and follow up with these over due course. But I think one thing that struck me from today's presentation is two very different approaches to introducing students to materials. Chris, you have 90 minutes, which I think is quite difficult anyway. in your lessons, but it was a really interesting story that you put behind the evolution of materials, and clearly the focus on polymers right at the end with the large expanse within the last few years is really interesting. And Richard, I mean, you just have a lot more time with the project and you've really delved in deeper there, as you've shown with a few Swiss Army knife examples. One question which I think is quite interesting, maybe for both of you, seeing as you're interested in polymers, is you mentioned, Chris, about expanding it into the eco audit potentially, or let's just focus on the eco properties. So when you're introducing students to the types of materials and polymers you can choose, how do you consider perhaps some of the implications of these choices, maybe the dangerous chemicals when you burn the plastics, or even through the manufacture? So I'll hand over to Chris first, if that makes sense, to just how would you introduce the choice of some of these materials, and then Richard, you can answer afterwards.
Yeah, sure. I think, first of all, putting materials into context, just to go back to what you said a second ago, is important because things don't happen in isolation. There's a tendency for students to get so focused on technical aspects, they forget that things happen within a world, within the real world. My background is steel making, and that evolved to meet certain challenges at certain times. And so there are reasons why things have evolved the way they are. And I try to give a bit of a background to that with the plastics too. So I think that's important for students to realize things are the way they are for a reason, and that doesn't mean they have to keep being the way they are. And indeed, that things are changing in the world these days, and so materials must necessarily change to keep up with that. Going back to the sort of dangerous products, the other thing I like to show to people when I introduce them to EduPack is that it's not a magic wand. It's not a magic piece of software that will tell you the answer. It is a very valuable tool to help you get information you need to help you answer a question, but it won't absolutely in and of itself tell you the answer. If someone says, I want to build an aeroplane, what material should I use for the wing strut, the sort of supporting structure of the wing? You can't just type that question into EduPack and get an answer. You have to use your scientific knowledge, your common sense, some logic, and then ask the right questions of EduPack. So you can't just say, give me all the polymers that don't produce dangerous substances. I'm just actually trying to answer the question by looking through the entry for some of the polymers. Certainly in the polymer database, it does highlight some dangers. For example, polyvinyl chloride, in the warning at the end, there's a warning that says that it produces, lead and cadmium stabilizers present concerns over disposal. So some of that information is in there, buried within the records of individual polymers. When it comes to burning, that's, I think, probably, to my knowledge, it's not a tick box, like, for example, critical materials. It says yes or no, does it contain 5% critical materials? I don't think there is a box, and I may be wrong, that says yes or no, it forms a hazardous product. But certainly that would be something that, with the information that is in EduPack, a student would hopefully be able to work out, or at least work out whether or not they need to investigate whether or not there are dangerous products.
Excellent. Yeah, I think you pretty much hit the nail on the head there. Richard, do you have anything else to add quickly to what Chris has just said?
My students live in a different situation, perhaps in a slightly different situation as far as they are concerned. They are bombarded with the subject of sustainability every day. But what I try to help them with the help of relying on EduPack, is to give them some figures they can work with, so they have some substance. Because all the discussion about sustainability suffers from lack of substance at some time. Yeah, how much energy is expended when you produce the material? How much energy do you need for processing the material? How much energy and CO2 are produced or used when you use the product? That's exactly the first questions being asked if you want to get aware of what you are doing. And that's what I try to help them with, to become aware what they are doing, and then they can make up their minds on their own. That's not my job to tell them. To tell them, you must not do that, you must not do that. That's usually where the discussion in Germany, at least right now, still ends. Yeah, you have this. You must be sustainable. That means you should not use plastics, and so on and so forth. These general rules. You should get away from that, and have figures at hand which help you to compare. If I do this, what will that mean? If I do that, what will the production of CO2 be like? And so on and so forth. So that's part of the work in the project, in the innovation projects which they are doing, the students, I mean, where this is really helpful, a really helpful tool. Waken again, it's a Swiss knife of its own, yeah? I would call it a Swiss knife. The sustainability, like in the eco-audit.
Excellent. I think, unfortunately, we're probably running out a bit of time here with questions. We started a little late, so sorry about that. But I think you both have... oh, no, it's fine, don't worry. But you both have had sort of a really nice complimentary sort of answer there to the question. And it really sort of shows that EduPack really is just a wonderful platform for discussion and a tangent to real life decision making. You both sort of nodded to the trade-offs that students will have to make in real life, and you both said there is no perfect answer. You have to learn to speak and discuss with one another, and that's what hopefully the software is there to provide. So with that rather nice conclusion, I think I just want to thank you both again today for joining us and presenting what you've been doing over with your courses. And for Lizzie, thank you ever so much as well for helping organise this. If you have anything else to add, go for it now. But if not, I think that will conclude our session today. And thank you very much.
Yeah, just a quick thank you from me as well. And if you have any questions, feel free to reach out to our team. We're happy to help. And thank you, Harriet.
Thank you so much.
Thank you, everybody.
Bye-bye.
Bye.